community.
Perfect. So that's why my talk is very introductory. Yeah, it's not. I thought Matthias Troya can later go deeper into issues. Yeah.
Great. So, shall we start, guys?
You tell me what I have to do.
Okay. So, hello, everybody. I'm not hearing you, Usama. Okay. So hello, I'm Dr. Tahar Webeh from the University of Constantine, principal investigator at Constantine Quantum Technologies and associate professor at the University of Constantine I in Algeria. Thank you for being here. I'm very happy to take part to the AI Summit Algiers, and I'm even more happy to introduce Professor Petruccione, who will be our speaker for this session. Professor Petruccione studied physics at the University of Freiburg and received his PhD in 1988. In 2004, he was appointed professor at theoretical physics at the University of KwaZulu-Natal in South Africa. In 2005, he was awarded an Innovation Fund grant to set up a Center for Quantum Technology. In 2007, he was granted the South African Research Chair for Quantum Information Processing and Communication. At present, Professor Petruccione is interim director of National Institute for Theoretical and Computational Science, NITEX, and professor of quantum computing at the School of Data Science and Computational Thinking at Stellenbosch University at South Africa. So Professor Petruccione is an elected member of the Academy of Science of South Africa, a fellow of the Royal Society of South Africa, and a fellow of the University of KwaZulu-Natal. Recently, he has been elected as fellow of the African Academy of Science. I've been very pleased to attend the ceremony last week in Cape Town. He has published about 180 papers in referred scientific journals. He is the co-author of monographs on the theory of open quantum systems, more than 7,000 citations. That was published in 2002. He also published a monograph with Maria Schuld on supervised learning with quantum computers, one of my favorite books in the field. Still a lot to say on Professor Petruccione, actually, awards and achievements, but I'm going to stop here, otherwise we will not have any time remaining for the talk. So thank you so much, Francesco, for accepting Constantine Quantum Technologies' invitation to take part to the AI Summit, and the floor is yours. Thank you.
Yeah, thank you very much, Taha, for the very, very friendly introduction. It's an absolute pleasure for me to be part of your very interesting event. And it's quite funny that I'm speaking to you from the other end of the continent. So it's really very nice to have these north-south connections in our part of the world. So thank you very much for the very kind invitation. I'm also very pleased to speak at this forum, which is more, from what I get, more addressed as computer scientists, because I've made already a few times. I taught a course in quantum computing to computer science students. And often they end up knowing more about quantum computing than the physics students. So I'm very, very pleased to be part of this. Thank you very much for the invitation. Yeah. Taha made me almost blush with the introductory comment and the bio, but I want to share with you something that I'm even more proud of, all the things that he mentioned. Yeah? And that is that the work with Maria and Ilya was quoted in a thriller. Yeah. And that's something really funny. Yeah. So thank you very much. Okay, for today, and I assume I was told I have roughly half an hour, 40 minutes, including the questions. This is the plan of my talk. Yeah, I will start with a few general comments on the future of computing that might be boring for you computer scientists. Then I will, just to warm you up to quantum machine learning, briefly give you a quick review of quantum computing and quantum algorithms, and then move a little bit towards the idea of quantum machine learning. If I don't waste too much time, I want to show you a minimal quantum machine learning algorithm. If we run out of time, I will skip to the next, which is probably one of the more common approaches at the moment, the variational quantum circuits, and then maybe conclude. So the future of computing, I'm preaching now to people that know it better than me, but it's quite obvious that the advances in AI go hand in hand with advances in hardware development. Yeah, all of the fancy things that we can do today, from DALL-E to ChatGPT, wouldn't be possible without GPUs. Yeah. And hopefully the hope is that one day in the not too distant future we might have universal quantum processors. Yeah, but what we have already, yeah, and this is essentially the worst case scenario. Yeah, a quantum devices that can already calculate parts of machine learning algorithm, for instance, the evaluation of kernels, very, very efficiently. Yeah, so that even today, it's not a waste of time to study quantum computing, because there are already worst case scenarios that are okay. Yeah. So even if we, for whatever reason, fail to build a universal quantum computer, there will definitely be space for dedicated quantum devices to speed up certain parts of numerical calculations. Yeah. If you look at computing from a very high level, yeah, you have essentially three approaches. Yeah? The classical one, the bits, which couple mathematics and information theory. You have the neural network inspired, biologically inspired approaches, biology and information. And what we are discussing here and today is essentially the physics plus information approach to computing. Yeah? And this is something that started more or less at the end of the last century. Yeah, it will be in the 80s of the last century, where quantum mechanics and information starting to merge, and building what we hope is a new discipline for the 21st century, quantum information science. Yeah, that has mainly three branches: the computing, the communication, and the metrology sensing branch. There are, of course, many other applications of these more modern quantum technologies, but these are probably the three the three major ones. Yeah? And in the high level context, everybody, at least in South Africa, probably in Algeria as well, everybody speaks about the fourth industrial revolution, but the goals of it might only be reached by exploiting the second quantum revolution. Yeah, the first quantum revolution was almost 100 years ago, when people like Einstein, Schrödinger, Heisenberg defined the theory of quantum mechanics. Yeah, but it was only in the 80s when the second quantum revolution started. Yeah? And that was when we developed the ability to manipulate single quantum objects. Yeah? So until the 80s, the standard textbook examples of quantum mechanics, hydrogen atom. Yeah? And nobody had ever seen a single hydrogen atom. Yeah? We always looked at ensembles of hydrogen, but the manipulation of a single atom, yeah, or a single photon or a single electron, that kick-started the second quantum revolution, started only in the 80s. Yeah? And here's a short timeline of quantum computing, just to show you how it went hand in hand with other trends. Yeah? As I said, quantum mechanics started in its current form almost exactly 100 years ago. Yeah? And that was way before Turing developed the universal Turing machine. before transistors. So one of the first real application of quantum mechanics was the transistors in the 40s, end of the 40s. And also after the Second World War, Shannon published the monumental work on the mathematical theory of information. Yeah? And those were probably big achievements of the Second World War from a scientific point of view, yeah, for obvious reasons. Yeah? And then in the 70s, 80s, this business of manipulating single quantum systems started. Yeah? And that's when Feynman, Richard Feynman, in a famous lecture, suggested that if you want to simulate nature at its fundamental level, which is quantum, it might be a good idea to develop a machine that operates according to the quantum rules. Yeah? Shortly afterwards, David Deutsch from Oxford did for quantum computers what Alan Turing did for classical computers. He showed that in principle it is possible to build a universal quantum computer that algorithmically solves problems. Yeah? But it took then almost another 10 years until Peter Shaw found the first useful quantum algorithm, yeah, which is the algorithm for decomposing large numbers in their prime factors, yeah? Which of course has a very interesting applications. Yeah? And it was the same Peter Shaw that also developed a few years later, showed that if you had a quantum computer, you could develop an algorithm for error correction. Yeah, because like classical computers, also quantum computers makes errors. Yeah? And you need some quantum error correction code. So in principle, you could say that Peter Shaw was the person that kickstarted this quantum computing business, because he gave us a useful algorithm and he showed that in principle we can correct errors of such a potential machine. Yeah? And then the race to build quantum computers started. Yeah, it started with very simple 2-qubit quantum computers using NMR technologies, and a few years ago, for just to mention one example, IBM put the first kind of commercial quantum computers in the cloud. Yeah, just a brief historical overview just to see the context of how it works. Yeah. So the basic idea of quantum computing, and you probably know, so that I can keep it short, is that you need a quantization procedure, yeah, for moving from the bit to the quantum bit, yeah, which nowadays everybody calls the qubit, yeah. And the transition is very simple. Just replace the 0 bit with the 0 cat, yeah. You use this bracket notation that is due to Dirac, and the 0 cat is essentially a 2-dimensional vector 1, 0, yeah. Similar procedure for 1 goes into 0, 1, 2-dimensional vector. Yeah? What makes quantum interesting is that there is something called the superposition principle, yeah? Which says that a general qubit state can be in a linear combination of the 0 and 1 state, with alpha and beta being complex numbers normalized to 1. Yeah? So that's the idea of the qubit. And you can represent the qubit on geometrically in what is called a Bloch sphere. Yeah? So every point on the surface of the Bloch sphere is a legal qubit state. Yeah? So with 0 at the North Pole and 1 at the South Pole. Yeah? And of course, you can parameterize it as it indicated there. Yeah? So and you see that the geometrical structure of the qubit is much, much richer than the geometrical structure of the bit, which is essentially a switch. Yeah? There is a current, there is no current. Yeah? And of course, you can do lots of things with the qubit that you can't do with the bit. Yeah? But let's skip over it. So what can you do with the qubit? Since the qubit is a quantum mechanical object, all the rules of quantum mechanics apply. Yeah? So essentially, if you want to study the evolution of a qubit, yeah? The Schrödinger equation applies. Yeah? And a simple integration of the Schrödinger equation, and if you're not familiar with it, doesn't matter. The only thing that is important is the equation in the blue box, yeah? Is that in order to calculate how the qubit evolves, you need to apply unitary operations. Yeah? You need to apply matrices where u times u dagger is equal to 1. Yeah? The other very important thing, and this is fundamental to understand just now how quantum gates operate. Yeah? is that for qubits, the same rules of measurements apply than in quantum mechanics. So if you have your qubit in a superposition, after a measurement, you get a probabilistic result. Yeah? The measurement will be either 0 with the probability alpha square or 1 with probability beta square. Yeah? So this is just standard quantum mechanics applied to the quantum unit of information. Yeah? Now, this is what you can do with the qubits. yeah, and this is a slide copied from the website of the gentleman listed here on the bottom right corner. Yeah? So if you have one qubit, essentially you can use rotations around X, Y, and Z axis, yeah, which are also known in quantum mechanics as the Pauli gates. Yeah? You can do also more fancy things, like for instance the Hadamard gate, and I will show you just now how that works. Yeah? It brings the qubit from a state 0 or 1 into a superposition. Yeah? And then there are, of course, multi-qubit gates. Yeah, the most famous of them being the C0. Yeah, and at the same time here you see the circuit symbol for the C0. Yeah, and there is a very famous theorem that says that in principle, the most general manipulation of qubits you can achieve by using single qubit gates, yeah, like X, Y, and Z, and C0s. Yeah. So and this is important if you want to build quantum computers, yeah, because it means that if you can build C0 gates and if you can build the Pauli gates, you can in principle build a quantum computer. Yeah. There are, of course, also multi-qubit gates, but let's leave it for now. Yeah. So altogether, the whole of quantum computing is essentially what you see here. Yeah, you need to prepare a register in a state of multiple qubits, yeah, indicated here by psi 0 to psi 1. Then you have a big unitary operation, which prepares another quantum state psi, and then you need to measure, and then you get some probabilistic results. So that the traditional gate model for quantum computing, yeah, is essentially maps the traditional full stack approach of classical computers. From you have a quantum algorithm, you need to design a quantum circuit on which you implement it. You need a compiler that sends it to the processor or to the simulator. Yeah, if you don't have access to a real quantum computer, and that's it. Yeah, just to mention it. There are also other approaches to quantum computing, yeah, and these are the so-called quantum annealers, and the most famous one being the one, and I have no financial interest involved, developed a Canadian company called D-Wave, yeah? But this is a specialized machine that in principle they're just annealing. Yeah, it's a machine that is very good at solving certain classes of optimization problems. Yeah? And the strategy here is a little bit different because you don't have this quantum circuit approach. Essentially, you need to encode your problem into a specific Hamiltonian, yeah, into a specific energy function, and then the machine finds the finds the minimum for you. Yeah? But in the following, I won't speak about this. Yeah? So you're a computer scientist, so you're probably interested in software. Yeah? This is a slide from several years ago that one of my former students wrote, Mark Fingerhut, on a paper, yeah, where they listed a little bit the older quantum computing software that was available at the moment, the open source one. Yeah? And you see there was already 4 years ago a lot of software. Yeah? In the meantime, there is even more. Yeah. Yeah. So let's see, just to move towards quantum computing and quantum machine learning. Yeah? Let's give a quick overview. You see, this is a slide that shows you a little bit the evolution over time of various quantum algorithms. Yeah? It started in the 90s, yeah, where David Deutsch, that I mentioned in the timeline, found a very simple algorithm that showed, in principle, a quantum advantage. Yeah? Then there were other interesting, I mentioned Peter Shor, around the same time, the quantum version of Fourier transform was developed, and so on and so forth. Yeah, so and let's say towards the 2010, a big boost was the discovery by Harro, Hasidim, and Lloyd of how to do linear algebra, essentially with quantum computers solving systems of linear equations, application to chemistry, to field theory, variational quantum eigensolvers are also almost 10 years old, yeah? Quantum approximate optimization, and so on and so forth. So there is a zoo of algorithms. There is even a website called the Quantum Algorithm Zoo, yeah? that lists all the known quantum algorithms so far. Yeah? But you know, if you look at this, it looks like it's overwhelming. Yeah, but in principle, all these approaches are quite structured. Yeah, because there are, I mentioned, for instance, the quantum version of the Fourier transform. Yeah, there are, let's call them tricks. Yeah, simple algorithm. Yeah, that you can use to define and design a little bit more complex algorithm like amplitude amplification, phase estimation, yeah, which are probably tools that you use in the proper algorithm, yeah, that you use in the algorithm for search, for the Shor algorithm, for linear algebra, and so on and so forth. Yeah, so it's fairly straightforward to develop a kind of a systematic approach to understanding quantum algorithm by starting with the most elementary building blocks and then putting it all together. So, sorry, let me check the time. Okay, I already spoke a lot. Let's look at the idea of quantum machine learning. Yeah? Quantum machine learning is essentially the intersection of machine learning and quantum computing. Yeah, not very surprising. Yeah? And it started this business essentially around just over 10 years ago, with a paper that I mentioned by Harro, Hasidim, and Lloyd, also often just mentioned as the HHL paper, yeah, in which it was shown how to solve linear systems of equation with quantum computers. Yeah? And that led to an explosion of papers in quantum machine learning. Yeah? So the basic idea is, of course, you know about classical machine learning, so I don't need to spend lots of time here. Yeah? Is how we find the quantum version, yeah, of supervised learning, of unsupervised learning, of reinforcement learning, and so forth. Yeah, and essentially, you need again a kind of a quantization procedure. Yeah, for instance, if you look at various classes of machine learning algorithms, like k-nearest neighbor, support vector machines, and so on, yeah, those are algorithms that use calculate distances, yeah, in order to do classification jobs, for instance. Yeah? and quantum mechanically, we know that quantum mechanics is always good at calculating distances, yeah? Because distances are essentially a scalar product, yeah, of the wave function. So it's a fairly straightforward to generalize those approaches. Yeah? Neural networks is a little bit more tricky because neural networks always use nonlinearities, yeah, to optimize. Yeah? And quantum mechanics is a linear theory. Yeah? So there is a kind of a disconnect there. Yeah? But I will show you just now how you can overcome this challenge. Yeah? Other approaches that are, let's say, more stochastic, yeah, or probabilistic, those can also fairly naturally be reformulated in the language of quantum mechanics, and that would be in the language of open quantum systems, yeah, because there is a Markovian theory of open Markov systems, so you can use the classical Markovian theory and somehow translate it into a quantum Markovian theory, yeah, so that is also possible, yeah. So another aspect that you have to keep in mind, speaking of quantum machine learning, is that we can classify the approaches depending on what data you have and what algorithms you have. Yeah. So the machine learning that you probably are taught traditionally, yeah, in your courses, your data is classical, and the machine learning algorithm is classical. Yeah. what I will mostly mention to you today is that you still want to analyze classical data, but you want to use a quantum algorithm for that. Yeah, but then there are also the cases where your data is quantum and your algorithm is classical, and also the case where your data is quantum and your algorithm is quantum. Yeah, so you need to be well aware in which class of algorithm of quantum machine learning you're operating. Yeah. So let me explain to you the challenges. Yeah. If you have your classical machine learning algorithm, yeah, you look at data set, yeah, and you want to make a prediction for, let's call for the new instance x tilde, yeah. So you input your data set into a prediction algorithm, and then for x tilde, the algorithm gives you some kind of prediction. Yeah? And you want to do the same in a quantum machine learning algorithm. Yeah? So you have the same data set, yeah? The same, let's say, a new instance for which you want to make a prediction. But now there is the fundamental problem, yeah? That quantum systems operate a little bit different. Yeah? First, you need to prepare the quantum state, then you have the unitary evolution, and if you want to measure and to find some numbers, yeah, you need to do a quantum measurement. Yeah? And I told you that quantum measurement is a bit different from measuring classical things because it's intrinsically probabilistic. Yeah? So what you need to do in the quantum machine learning algorithm in the middle of the slide, yeah, you need to encode the data set into a quantum state. Yeah? And that is a discipline on its own. Yeah? Then you need to apply your quantum algorithm. Yeah? Then you need to measure your quantum state, and from there extrapolate your prediction. Yeah? So you see what additional steps we need to do. Yeah? We need to encode the data set into a quantum state, so into qubits. Yeah? So you need to take your classical data and encode it somehow into qubits. Yeah? Then you can apply your quantum machine learning unitary machinery. Yeah? But then you need to measure your quantum state, and out of the probabilistic result of the measurement, of the quantum measurement, make your prediction for y tilde. Yeah? So this need to be kept in mind. Yeah? So there are various steps where it could turn out that quantum machine learning is useless. Yeah? Because, for instance, if encoding the data set in a quantum states requires lots of effort, yeah? Yeah? The advantages of the quantum algorithm could be destroyed. Yeah? So there are various steps that need to work properly. Yeah? But we know more or less how to do it. Yeah? So how much time do I still have before I continue here? Can you please let me know?
Hey.
Hello.
Do you hear me?
Yes,
Do you hear me?
Yes.
Still 30 minutes. You have more 30 minutes for.
Okay, perfect. Thank you very much. Okay.
You're welcome.
Then, yeah, thank you. Then I probably won't need more than 15. Then let me show you briefly the basic idea of a minimal quantum machine learning circuit, as simple as it can get. Yeah, just to show you how it all comes together. Yeah. So as using essentially the same notation as before, we have a data set x1 to xm. Every x has a label. Yeah, just to keep things simple, the label y is -1 or 1, and we want to find the label of a new input x tilde. Yeah, that's what we want to solve. Yeah. And let me show you the result, yeah, of this very simple quantum machine learning circuit. Yeah, we just implement a very simple distance-based classifier. Yeah, that is essentially a very simple kernel. Yeah, that is like 1 minus x squared. Yeah, very simple distance measure. Yeah, that's what we want to implement. And the basic idea is the following one. So first of all, let me show you how you can put the data into the quantum computer. Yeah? So one idea is that you encode the classical data into the amplitudes of a quantum system. Yeah. For instance, if you have your data set X, yeah, let's say you normalize X to be 1, yeah, and then you prepare your wave function in such a way that the x's, xi, are the amplitudes or the coefficients of your qubits, yeah, and the qubits, and you have n qubits, yeah, so each qubit has an amplitude xi, yeah, so that is a way to encode classical data into a quantum state. Yeah, there are other ways, but let's keep it simple, yeah. Then you need to prepare your state. Yeah, and one possibility is to create a superposition. Yeah, you see here you have a superposition of your prepared state psi psi xm's. Yeah, the sum over all labels. You have an index registers and you have your label register. That's one possibility. Yeah. And now the most simple classification scheme is just to use a Hadamard gate. Yeah, I briefly mentioned it at the beginning. It's just a single qubit gate that creates a superposition. So if your qubit is 0, the Hadamard gate creates a superposition of 0 and 1. And if the qubit is 1, it creates a superposition of 0 minus 1. Yeah. Yeah. And after that you just measure, yeah, and that I probably just make it simple. Let's keep and this simple structure, yeah, allows you. I think I mentioned some of the reference, yeah, to implement the simple binary distance classifier that I showed you at the beginning. Yeah, so this is very, very, very simple. Yeah. And we applied in this paper, which was written, I remember, 5-6 years ago, yeah, the standard iris flower data set. And if you do all the standard procedure, it turns out that it works. Yeah. But what I want to show you, which is very important, yeah, is that if you look at the red box here on the quantum circuit, you see that the classification part is quite easy. Yeah, you just have one gate and a few measurements. Yeah? Whereas the preparation of the state vector to begin the classification, yeah, is quite involved. Yeah. So to input the data into your quantum computer requires some effort. Yeah. And here you see in this figure there are other boxes. Yeah. And these boxes, sorry, I show you them here. Yeah, are here. So those boxes are made of many more gates. Yeah. So the point is that let's go back here, for instance. Yeah, that even if the pure classification step is simple, inputting the data in your quantum computer might require some effort. Of course, this was 5 years ago, so everything was more or less done by hand. Yeah, and now there are many tools to facilitate that. Yeah, but it's a critical, time-consuming part of your algorithm, and also a part where many errors can be made. Now, maybe in the remaining 10 minutes, let me just give you an insight on the more modern approaches to machine learning. Yeah, so the basic idea of doing machine learning on quantum computers is using variational quantum algorithms. Yeah, and these are essentially hybrid approaches, yeah, where you have you see here on the left your register of qubits, then you have a processing step and your measurement step. Yeah. Out of your measurement and the average of repeating this procedure many times, you can calculate a cost function with certain parameters. You optimize the cost function, and you input again the parameter in the processing unit ansatz, in the W of theta. Yeah. So there is a feedback scheme. Yeah, and you do it a sufficient number of times until the training is done, and you achieve what you wanted to achieve. Yeah. So this is a typical hybrid approach that is well suited for the quantum computers that we have at the moment. These so-called noisy intermediate state quantum computers. And noisy because they don't have enough qubits to implement error correction. So these are essentially quantum computers without safety net. If you do an error, but if the algorithm produces error because of the noise and so on and so forth, it's just bad luck. There is no way of fixing it. So this is the basic idea of this hybrid variational quantum algorithm. There is a specific class of variational quantum hybrid solvers called VQEs. Use the same principle as before. And these are specifically designed to minimize expectation values of certain Hamiltonians, if you want. And you see here on the left the basic idea. It's the same variational procedure. You use an average over your ensemble, and you calculate the expectation value of the Hamiltonian. And you have a parameter theta, and you minimize it, and you find the minimum. So this is the standard approach. So this would be an example. If your Hamiltonian has a particularly nice structure, like it is a sum of Hamiltonians, you can write it all nicely, and it becomes even much simpler. So these are the variational quantum eigensolver. And here's a very, very simple example just to show you how it works. So you have here, you have your qubit in state 0, and you measure sigma z. So then you calculate the expectation value, and it's just 1. And now you put an x in between, an x gate in between. You calculate the expectation value, and it turns out to be -1. And now we want to do the simple variational example. Also, you have a qubit, you have 2 rotations, one around x, one around y, with an angle θ1 and an angle θ2, and you measure the expectation value of sigma z. And if you do the maths, it's just multiplication of 2 times 2 matrices. It's not so difficult. You can calculate the expectation value analytically. But now you have 2 parameters, and you might want to choose them optimally. So now you can do the basic idea of the variational algorithm. You need to define a cost function, and you update it, and so on and so forth. And for instance, a cost function, you can minimize the cost function, for instance, using traditional differentiation. You can use automatic differentiation, which is then a combination of classical and quantum computation. And for instance, a famous approach is the so-called parameter shift rule, where you essentially you differentiate by choosing different parameters in the quantum circuit. You calculate the partial derivative by using your circuit with parameter mu plus s or parameter mu minus s, and then you can calculate automatically the partial derivative. So this is the basic idea. Another important thing, the distinction to do, is that you have deterministic quantum machine learning models that are, for instance, useful for supervised learning. And then you have also probabilistic quantum machine learning models. The typical structure of these deterministic quantum machine learning models in this variational business is that, again, you have your input qubits in state 0. Then you have a block in your circuit where you do the data embedding. You need to embed the data in your quantum state so that you can push them then forward to your parameterization block, where you do the optimization, then you measure, you average, and so on and so forth. And you get an expectation value as an output. This is a typical structure. And for instance, and then you have, for instance, I mentioned deterministic, and there's also probabilistic, which is, for instance, also used for supervised learning, where you have your same embedding block, your same parameterized block. you just perform the measurement on your qubits, and you can use it to estimate, for instance, conditional distributions, yeah? Instead of expectation value. Yeah? You just keep the average step of the deterministic one. Yeah? One typical example would be, for instance, the Born machine, yeah? For unsupervised learning, yeah? Where measurement lead to the sampling of a distribution, for instance. Yeah? And yeah, just a simple example. Yeah. Let me show you maybe pictorially how this works. Yeah? For instance, in an example similar to the one that I showed you before, yeah, you start with your classical data. Yeah, you need to map them on the Bloch sphere. Yeah, like it's indicated here. So your data points are somewhere on the Bloch sphere. Yeah, then you do the rotation and you map. And you sort of rotate your points on the Bloch sphere, yeah. And then by applying the measurement, you define the definition boundary. So if you do it, let's say at the level of a 1 qubit, I should have put this slide a little bit before. Sorry. You can have even a kind of a pictorial description of what is going on, yeah? which I think is quite nice. In higher dimension, of course, it becomes more difficult. So now, let's do the jump to deep learning, yeah, because that's what everybody is interested in. Yeah, deep learning is essentially also a variational circuit, yeah, but a little bit more of a more involved variational circuit, yeah, because in the bottom half of the slide you see the typical kind of neural network structure of a deep neural network, yeah, and we need to map it to a unitary circuit. Yeah, so we have again the same steps as before. Yeah, we have the qubit in 0 state. We have the S step where we embed the data in the quantum states, and then we can have a mixture of layers of fixed gate and layers with parameters. Yeah, here I just drawn it with 4 layers, 2 fixed and 2 trainable. Yeah, and then you do the same gadget as procedure as before with the variational circuits. Yeah? The point is that it's in the last step where you measure that the nonlinearity kicks in. Yeah. So, and this is kind of the workaround of quantum machine learning to introduce something nonlinear for these deep linear neural networks. Yeah? So you see, you can fairly nicely map a deep linear neural network to a variational quantum circuit with this trick of having layers of gates, some of them having a tunable parameter. Yeah? So conclusion, let me share maybe a few thoughts that were also discussed recently at the World Science Forum, where we had a session on a proposed open quantum institute. Yeah? And the basic idea, of course, there is that we should be able to use quantum computing for sustainable development. Yeah? And I've been working for the last year and a half or so with GESDA, which is the Geneva Science and Diplomacy Anticipator, and we try to develop together. Also, Matthias Troja is chairing this group. Yeah, you will hear from him later. Cases where quantum computer can help us solve sustainable development goal problems. Yeah? One of the test cases, yeah, is, for instance, the development of new carbon capture materials. Yeah? And this is because we know, I didn't speak about it, that quantum computers are also very good at solving quantum chemistry problems. Yeah? So the idea is to design algorithms that can help you design new materials. Yeah? Another possibility of simulation would be tackling the problem of antibiotics in wastewater. Yeah? It's also a problem that is highly complex and where possibly quantum computers can help us find a solution. Yeah? A problem that is super relevant, yeah? And is the production of fertilizers. And you all know that producing fertilizers is a very expensive business, because you need very high temperatures, you need very high pressures, and so on and so forth. But we all know that bacteria do it essentially for free in the soil. But we don't understand really that biochemistry. So the hope here is that using quantum computers, we might be able to develop more eco-friendly, cheaper and ecologically more responsible fertilizer. Just as another example. Another example that is also interesting is the sustainable food production. Because we know that because of climate change, it might not be possible to grow something where you were used to grow. So you need to identify other places geographically where to grow certain crops and so on and so forth. And then how to, so that you see, this could be at a global scale, a very, very challenging problem to optimize. And here again, because we know that quantum computers are good at optimization, it could be a very interesting test case to discuss. Similar difficulty is also and we also all suffered from COVID for the last 2-3 years. And we all realize that the vaccine distribution can be a serious issue. And in particular, if you live on the African continent, we were not in the first row when it came to distribute vaccines. So this is also a highly complex optimization problem where quantum computers might have. And it's not only relevant for COVID vaccine, it's relevant for all classes of possible vaccinations. So these are just some of the ideas of why it could be interesting for young people to get involved in quantum computing, because there is still lots of hope that they will help us solve a very interesting problem that affect us all. So thank you. Thank you very much for your attention. And if you have questions, I'm here to answer them. Thank you very much.
Thank you very much, Francesco. Great
Pleasure.
talk. Thanks a lot. Lots of things to learn, lots of things to understand. And let's start with some questions. So Nuha is asking, I perfectly understand that Hadamard provokes superposition and control not do entanglement, but I want to know how to choose the type of gate to use in quantum circuits and their order.
Okay. I guess there is no magic rule. My advice would be, would be to start just playing with this stuff. You need to start. You need to develop a little bit of an intuition for what's going on. And maybe even before starting to learn programming languages for quantum computers, and you can use the one that you already know. I would just use pen and paper, and do a little bit of 2 × 2 matrices multiplications, to see what leads to what, just to develop the intuitive physical feeling for what is going on. And once you know that, then you can start, like I showed you in one of the slides, to start to understand how the basic building blocks of quantum computers work. How, for instance, amplitude amplification works. Those are very simple applications of, for instance, of the Hadamard gate. And that then are relevant to understand, for instance, how search algorithms work. So I wouldn't start by learning search. Start learning the basic foundational blocks of quantum algorithms. I think that's the best advice that I can give you. Might be disappointing, but that's how. At least that's how I learned it.
Great. So Ilyas is asking, in which case we decide to do measurement on all qubits or only on some of them?
Yeah, that's also an interesting question. You know, sometimes you want to, and again, there are very simple basic algorithms where you can see why you want to do that, yeah? Because sometimes, depending on the measurement of one qubit, you want to do something else on another qubit, yeah? That would be, for instance, one reason why you don't want to measure them all at the same time, yeah? For instance, you want to measure, let's say, the first qubit, and depending on the outcome of the first qubit, you know that you need to apply this or that on the other qubit to obtain whatever, yeah? Again, you know, there is no real generic answer, probably, yeah? For instance, you saw some of the variation of quantum algorithm. There you want to measure them all because you want to calculate the averages. Yeah? But there are other cases where, for instance, what would be the simplest cases? Maybe in the circuit for teleportation. Yeah, if you want to teleport one qubit, yeah, you will have the situation where you measure one qubit, and depending on the outcome of the measurement, you do something else on the other qubit, and then you manage to teleport the qubit. Yeah. Again, I fear there is no generic answer to your question. Yeah, you know, like machine learning, there's lots of experience and art involved. Yeah.
Great, thanks. So Elias is asking also on how to choose the right data encoding technique to use.
That's also interesting. You know, as I mentioned, the different situation might imply different data encoding solutions. I showed you the most simple one where you encode it in the amplitude, but there are others. Yeah. And depending on the problem, one might be better than the other, or the other way around. Yeah.
Omar Zahia is asking, so I would like to know about the difference between the model using quantum machine learning and the machine learning model in terms of accuracy.
Interesting problem.
It's the whole question, I guess.
You know, I can tell you a funny anecdote. Yeah? A few years ago, I gave a talk at one of the big, I don't want to mention name, hardware companies, let's put it that way, yeah? Where some, and all those companies have their machine learning gurus, yeah? And I showed them the simple example of quantum machine learning, like I did it with you, and I'm starting speaking of the iris data set, yeah? And those guys stood up and left. Yeah. You know, the accuracy is an issue, because at the moment we have only these noisy intermediate states quantum computers, and as I mentioned, they don't have enough qubits to do error corrections. Yeah? So they accumulate errors. You know, the bigger your quantum the deeper your quantum computation is, the more CNOTs you apply, yeah? The more errors you do, and the results are less accurate. Yeah. There are techniques to minimize the errors, yeah? But there is no proper error correction such integrated in the quantum computing system. Yeah. So you know, for high accuracy applications, it will require maybe some time until we can put our hands on many more qubits. Yeah? But I know of cases on cases in quantum chemistry computations where the accuracy can be very high. Yeah. But there is probably because, you know, the quantum computer uses the same rules of quantum mechanics as the quantum chemistry reaction. Yeah. So there are cases there where I've seen that you can achieve high accuracy, even maybe better than with classical algorithm in instances.
Great. I have a question on the same sense, actually. So you have evoked the fact that we can apply right now variational quantum algorithms on NISQ computers, but those computers don't have like error correction codes which are such efficient. So suppose that we have done that, we have applied, or we have achieve the variational quantum algorithms on a NISQ computer. Is there any techniques available right now to, at the end, estimate how accurate is the calculation or is the training?
Yes, there are error models. For instance, if you use Qiskit, Qiskit provides you with error models, yeah, that you can use to study those issues. Yeah.
Great. So Nuha is asking, in which case we choose to use ancilla qubit or not?
Same answer as before. It always depends what you want to do. Yeah. For instance, in the simple machine learning that I showed you, you need an ancilla qubit, yeah, to achieve your goal. But there are cases where you can do without. Yeah.
Great. Munia is asking, what advice do you give for a person with machine learning background to start quantum machine learning? And I'm going to go in the same sense too, and I'm going to ask you, what is your approach, knowing that you are teaching computer scientists? What is your approach to convince computer scientists about the role they can have in quantum computing? And also, what do you have any kind of basic references for computer scientists with machine learning background to get started with quantum machine learning?
I mean, the basic approach, what I do when I teach quantum computing and then machine learning to the computer science students, I just start with 1 qubit. Yeah, we do everything that we can do more or less with 1 qubit, because physicists maybe have studied quantum mechanics in first year, in second year, in third year, fourth year. They have a feeling for what quantum mechanics can do. Yeah. And computer scientists need to develop it, but at the same time, they don't want to read the standard books on quantum mechanics. Yeah? So it's important to start, understanding more or less what is qubit beast can do and cannot do. Yeah, just by playing around a little bit, you can, study how the gates operated, looking at the Bloch sphere and so on. And then you move to qubits. And then you can already start understanding, with 2 qubits and a CNOT, you can start playing around with entanglement, yeah, which is the resource that you use in quantum, one of the resources that you use in quantum computing that you don't have in classical computers. Yeah, so entanglement is a form of a very strong correlation that is stronger than any classical correlation that you could have. Yeah, that you don't have in classical machine learning. There is no entanglement there. Yeah, but already with 2 qubits, you can play with entanglement. Yeah, and see what entanglement can do. Yeah. And once you understand 2 qubits, then the sky is the limit. Yeah, because as I told you, with single qubit gate and CNOT, you can construct any quantum algorithm. Yeah, and for the CNOT, you need 2. So once you understand 1 qubit, 2 qubit, then the sky is the limit. Then you can develop, you can understand all the basic tools of quantum computing and put them together to simulate more complicated things. Yeah.
Great. And this was part of the workshops that have been presented by Constantine Quantum Technologies at EASY in last October with the Qiskit.
Okay. Excellent. Well done.
With this, and we aim to do this again and again as far as people are. So Francesco, I think we still have time for 1 or 2 other questions. So I'm going to ask you, is there a class of problems which seem to be more efficiently solved using quantum machine learning than others?
Classification problems are good. Problems that support vector machine can solve are good. Yeah. And things like that. Yeah. So these variational quantum algorithms are quite a powerful tool. Yeah. But I see on the screen there is another question about cloud platforms. Yeah.
Yes, exactly. So
all major vendors, yeah, IBM, Google, Amazon, yeah, they all Microsoft, they all have cloud solutions. Yeah. And Taha mentioned Qiskit, yeah, the IBM Quantum Cloud has also a freely accessible quantum machines in the cloud, yeah. But you know, the reality is that if you want to practice with 5-10 qubits, you can simulate it on your laptop. Yeah. So you don't really need to use the quantum computing hardware. Yeah, you can implement a simple emulator on your laptop. Yeah. If you have hundreds of qubits, you can't do it anymore on your laptop. Yeah, I think by 30 or so that it starts getting critical. Yeah, but if you just want to play with 10 qubits, you can easily do it on your laptop. Yeah.
Great, we have reached an hour already. It was amazing. Thank you very much, Francesco, for your talk and for answering the questions. Thanks to the attendants for the interesting questions. Thanks for the School of AI Algiers for this very interesting event, and hope to see you again. Thanks a lot, Francesco. Thanks very much.
Absolute pleasure. It was great to be here, and the best for the rest of your school.
Thank you so much for the amazing talk. Do you hear me?
Yes.
Yes. Thank you very much.
Okay. It was really amazing. We also want to thank CQTech for the support. They were the main reason why we could invite you, Mr. Petruccione. Thank you very much. We would like to make this another talk or maybe more because the experience perfect. Thank you very much. Also, the team of School of AI want to give you really some good feedback that they enjoyed and learn a lot from your presentation.
Thank you very much. Thank you very much. And I hope that hopefully soon we will meet in person.
Yeah, why not? Why not? We are working on that.
Yeah, why not? Yeah.
That will be great.
It will be perfect.
Thank you.
Thank you so much.
Thank you very much. And all the best for the rest of the school. Yeah.
Thank you.
Bye. Bye-bye.